Okay, guys. So today I'm gonna be recording and posting 3 videos. The lesson 3, 4, and 5 in torque. These are the only ones we're gonna do. We're gonna drop off lesson 6, and basically lesson 3, 4, and 5 are just specific examples of particular kinds of questions. So this lesson is gonna look at static equilibrium. We've defined it before. When we talk in dynamics, when we talked about forces up equaling forces down, and forces left equals forces right, and then we used all those set of assumptions to derive our solutions to a couple different kinds of problems. We're going to add to this the ideas of the torques being balanced as well. So between all the forces being balanced, all the torques being balanced, we're going to use those sets of assumptions to solve particular kinds of problems. So the first one is this. We've got a beam. I think this lesson is all on particular kinds of beam problems. Lesson 4 is all about one sec. Lesson 4 is about beam problems in specific, and lesson 5 is about ladder problems specifically. This particular lesson is just going to be about how we use these techniques in general. So, first example, we have a beam of length 4 meters. It has a weight of 50 newtons. It's pivoted at the middle. So, we're going to draw this. There's my 4-meter beam. We're told that it's pivoted at the middle. So, I'm going to draw my pivot there. And then we're going to draw our free body diagram. So we're going to add all of our forces to it just from the beam. So there's a normal force up. We don't know what that value is yet. We know that we're going to assume, they haven't told us, but we're going to assume that the beam is uniform because they haven't told us otherwise. So that means force of gravity acts at the middle. The weight is 50 newtons, so that is the force of gravity. And we know this whole beam is 4 meters long. Cool, so that's what we know so far. We've got a 200 Newton weight is halfway between the pivot and one of the ends. We don't know which end. And then the question is, where should we place a 100 Newton weight to balance the beam, and what is the force exerted by the support on the beam when the beam is balanced? So we don't know where these objects are, so we're just going to start placing them and see what happens. So this 200 Newton weight is halfway between the pivot and one end. It doesn't matter if you use the left side or the right side, because if you put it on the left and then walk around the beam and look at it, it'll be on the right side. So that part is arbitrary. It doesn't matter. So I'm going to put it over here. It has a 200 Newton. It's 200 newtons. So Fg here is 200 newtons. And we know the distance. We know it's a 4-meter beam, so it's 2 meters from the pivot to the end. So if this is halfway between, then this is going to be 1 meter here. So this distance here is 1 meter. So we're going to have to place, we're told that we're placing a 100 Newton weight to balance the beam on this pivot. And so I hope it goes without saying that the 100 Newton weight is going to have to go over here to balance the torque created by this guy here, because the weight of the beam, because the pivot's at the same place as gravity's acting on the beam itself isn't actually going to be contributing to the torques at all. So we're going to have to put an object over here somewhere. We're told it has a weight of 100 newtons, and we want to know what this distance here is. I think we've got everything. So there's 2 sets of questions. The first is, where should we place the beam? And the second is, what is the force exerted by the support on the beam? And so there's 2 pieces here. If this thing's in static equilibrium, we know all these things are true. So we've got forces left equals forces right. We've got forces up equal forces down, and my torques clockwise have to equal my torques counterclockwise. Left and right isn't going to give us anything, because all of my forces are up or down or creating torques, so don't need it. What we can jump straight to, though, is the idea that our forces up equals forces down. Well, there's only one force up and there's 3 forces down. So we've got our Fn acting up. We actually solve the second half of the problem first. Fn is acting up. We've got a 200 Newton force acting down, a 50 and a 100. So my normal force is going to be 200 plus 50 plus 100. So Fn, the force exerted by the support on the beam, is just 350 newtons. And now we can use the torques to figure out what the distance here is. Should be relatively straightforward. Just extensions of the stuff that we did in the last couple lessons. So my clockwise torque, so which one of these is creating a clockwise torque? This guy here is clockwise. So I'm going to have my 200 times 1 is going to equal, and this guy's over here is counterclockwise, 100 times d. Just if we torque equals force perpendicular times distance. So we're going to get 200 divided by 100 equals d, so 2 meters equals d. So what does that tell us? Well, this object has to be placed 2 meters from the pivot. Pivot's right there in the middle, so 2 meters out, it's going to have to be placed right here at the end. That's it. Relatively straightforward, I think. Just a couple more examples, and then give you guys some practice. So example 2, a 45 kilogram person walks up to the end of a 10 kilogram diving board. We want to know which of the following is the correct free body diagram for the diving board, because these problems are going to require really that you understand how the free body diagrams work. So let's just start drawing these things in here. We're definitely going to have force of gravity down on this person here. So that Fg is going to be 45 times 9.8 is 441 newtons. Just draw them all in and see what we got. We're going to have the way it's drawn, I mean, you can see that it's uniform. It's a 10 kilogram uniform 3.5 or 3 3/4 meter long diving board. So right there in the middle, we're going to have an Fg there of 10 times 9.8. So the force of gravity acting on the board itself is going to be 90 newtons. Now the question is this: how are these two things creating or acting on the board? What forces are they creating? So if we think about what's happening here, this guy is falling. Well, the force of gravity here is going to want to make this end of the board tip down like this. With this particular piece here, what's it going to do? Well, if we put a dude here and this support remains stationary, this is going to fall here. What this support is doing is it's pushing up on the diving board here. It's preventing this end from falling. So this particular support is actually creating an upward force. I'm going to call that a normal force. It's the force of the board resting on this guy. And then, well, what's this support have to do here then? If this is pushing up as a rest, if you've ever been on a diving board before, you know that the whole thing doesn't flip over and smack you in the head every time you go for a jump. So what this board has to do, or the support rather has to do, is pull down on this end of the board so that you can actually get the spring that you want here. So this particular support has to have a force downwards. It's pulling downwards on this end. We'll call that an applied force. It's pulling down on this end to prevent the board from jumping up and smacking you in the back of the head as you jump. So the correct free body diagram is going to be this guy here. The reason I went through and actually did all the calculations is because example 3 is coming. We'll zoom this out a little bit here. And example 3 says, for the board above, use the first support as a pivot, write a balanced equation, and find the force exerted by the second support. So in this particular question, they've told us what they want to do. They want this to be the pivot. And so we can use that as the pivot to eliminate this force, and then use torques to find the normal force based on the other two, if that makes any sense. So here we go. We've got the clockwise torques equal the counterclockwise torques. That's my pivot. We're going to have which forces are going to be clockwise, well, which ones are counterclockwise. If this is where my pivot is, these two are going to drag this thing down, causing it to swing like that. So these two are going to be clockwise. So I'm going to have 98 Newton force. Do we know the distance here? Yeah, well, this particular support is acting on, we're told that there's a 1 meter distance here. This pivot is 1 meter from the end here. So we need the distance from the pivot at the end to here. Well, halfway from the end to here is 1.875. So that's going to be the 1.875 is going to be the distance from the pivot. 1.875. It's half of 3.75. So 98 times that is the torque created by that force there. I'll slide this up here a little bit. We're going to add to that the torque created by this force here. So 441 times 3.75. And that's going to equal my counterclockwise torque, which is going to be created by this force here. This force is pushing up. So if it were the only one here, it would drive the board up and backwards. So we're going to get my normal force, Fn, from the second support times 1, the distance from the force, where the force is acting, to the pivot. So we can find relatively straightforward that Fn is going to equal this 98 times 1.875 plus 441 times 3.75. It's going to give us an Fn of 1837.5 newtons. So that is, that's the first part of this question. The force exerted by the second support is there. And now we want to know, now we've got this here. Let's write that in. 1837.5. So the last piece to this question, the second last piece, part B, is write a balanced force equation and find the force exerted by the first support. Generally speaking, diving boards are static. They're stationary. They're not supposed to jump out into the water by themselves. When you're standing on the end, you want these things to be stationary. So what we're going to do here is we're going to use the ideas that my upward forces are going to balance my downward forces, because again, this thing is in static equilibrium. So we're going to have my forces up equal my forces down, which means Fn is going to equal, now my downward forces are the applied force from this support, the 98 Newton force of gravity from the beam, and the 441 Newton force of gravity from you on the end. We could have put Fn in here. We know what it is. It's 1837.5, so that's going to equal Fa plus 98 plus 441. So we're going to get the F applied from that first support is going to be 1837.5 minus 98 minus 441. So that's going to give us 1298.5 newtons. We could have gone through and done this a different way. What we could have done is we could have moved the pivot to any of these other locations. We could have put it here and then used these two, the torques created by these two forces and the torque created by this one. To figure out what the force applied is, we could have moved it out. We could have put the pivot right here, and we could have used these two. Then would become my clockwise torques, because this guy would make them spin up and this guy would make them spin down. and then this guy would spin counterclockwise. Or we could have put the pivot here and said, okay, well, these two are going to be the ones that drive down, and this is the one that's going to drive it up. It doesn't matter which way we would have actually approached that. So we could have done part B a whole bunch of different ways. Do one more example for you here, and that'll be it for this lesson. So example 4, we've got a beam shown below, right there. It's 12 meters long, has a mass of 5 kilos. We want to know the angle theta, that guy there, between the tension in that cord and the beam itself, and we want to find the tension in the first cable. So let's label some stuff here. We're going to call this is going to be T1. We know T2 equals this. This is theta. You should all be familiar with theta at this point. What you may not be familiar with is this guy here. This is phi. Phi is another Greek letter we use as a variable for an unknown angle. Basically, we use him like Basically, we use him like these guys like x's and y's. When we have multiple things we don't know, we have to use different letters because we can't assume that they're all the same letter. I couldn't use theta here because that would imply that these two angles are the same, and they're not. So let's draw a free body diagram on this thing. We know that we've got a force going up this way. We know that it's 75 newtons. We're looking for the force right there in tension 1. And the only other force acting on this object here is going to be the force of gravity downwards from the center of the beam. So this is going to be Fg, and we actually put a value to this. We know that this thing weighs 5 kilos, so 5 times 9.8 is going to give us a force of gravity of 49 newtons, or a weight of 49 newtons. This is the free body diagram. What we can do now is we could actually start to break, and what we're going to have to do is we're going to have to break this guy up into components. We're going to have to break both these guys up into components, actually. And the reason for that is this. Because these ropes now are acting off at angles, this rope, if we snip this guy, this rope would pull this beam over. It would slide down and over. And so there has to be a horizontal force acting here. Likewise, if this guy snapped, this thing would slide down and over. So there'd have to be a horizontal force here. We're going to have to start using the fact, in the previous questions, we only ever used up equals down, and my torques were equal because we didn't have left and right forces, but now we do, so we have to take those into account. So this guy here, I'm going to call this T2y, and we're going to call this T2x. I could have called them parallel perpendicular, doesn't really matter. So this guy here is going to be 75 sine theta, and this guy here is going to be 75 cos theta. I'm going to call this T1x, and this is going to be T1y, and so this is going to equal T1 cos phi, and this one's going to be T1 sine phi. So this is everything that we've got here, and we know this thing is in equilibrium. So it's in static equilibrium. And that's going to tell us three things. It's going to tell us static equilibrium implies that my forces left equal my forces right. My forces up are going to equal my forces down. They have to be balanced, otherwise this thing would be moving. And my torques clockwise have to equal my torques counterclockwise. And now what we've got to do is we've got to go through and we've got to find, well, we want to find the angle theta, and we want to find the tension in the first cable. So there's a lot we've got to do here. So based on this thing being in static equilibrium, we know a few things here. If my forces left equals my forces right, there's only two forces acting in that plane. The force acting left is this guy here, and the force acting right is this guy here. So we know, based on the fact that left equals right, that T1 cos phi is going to equal 75 cos theta. Not a lot we can do with that, with this at this point. I should put it in here, T1x equals T2x. So then up equals down. There's two forces acting up, so the two forces acting up have to add up to my force acting down. So I'm going to have T1y plus T2y are going to equal Fg, and so I can put in my expressions for T1y and T2y. T1y is T1 sine phi plus T2y is 75 sine theta, and that's going to equal 49. And now my torques. My torques. We don't have a pivot here yet. So we can't really start talking about torques until we choose where to place this thing. This is where we're going to start. I've mentioned it once before, and I'll mention it here again. The idea of weaponizing the pivot. What I mean by that is this, is we're going to use it to eliminate a torque from a force we don't know. Okay. And so there's only one force here that we don't know. We don't know what tension 1 is, and so that is where we're going to place the pivot. If we place the pivot here, what that allows us to do is it allows us to look at torques while ignoring that force. Because again, if we remember, a torque is a force times a distance, and the distance is the distance from where the force acts to where, I'll put this in here, torque equals a force times a distance. And actually it'll be the sine and times the sine of the angle between them. So if the distance between the pivot and the force acting is 0, there is no torque from that force, i.e. this guy here. If that's where my pivot is placed, there's going to be no torque from this force here. Because we don't know that force, we want to put the pivot there. So let's use what we've got by where that by locating it there, and let's manipulate the torques here. So my clockwise torque is going to be what? If that's where my pivot is, this force is going to make it swing clockwise. So I'm going to get Fg times, well, we know this is 12 meters long, and this is 2 meters. This would have been 6, so this distance here is 4 meters. So Fg times 4 is going to equal, now we can use two expressions here. It's either Fd sine theta or F perpendicular times, well, actually this should have been an R. Fr sine theta times Fr. The perpendicular one is 75 sine theta, and we got to remember that just because I've drawn my component over here, it's acting at that location right there. So we've got F perpendicular, which is going to be 75 sine theta, and then the distance from the pivot to where this force is acting, this is 6 meters, so this is 4 meters, and we're told that this is 4 meters, which means that has to be 2 meters. If that's 2 meters, then this thing has to be 6 meters here. And I could have put Fg in there, I guess. So 49 times 4 is going to equal 75 sine theta times 6. Now, we can see here in that torque equation, there's only one piece of information we don't know. We don't know theta. So that's going to be really easy to solve. So sine theta is going to equal 49 times 4 divided by 75 times 6. So theta is going to equal the sine inverse of that mess. I'll slide this down here so you can see what I've done. So we're going to have the sine inverse of 49 times 4 divided by 75 times 6. Be careful how you punch that into your calculator. We're going to get an angle here of 25.82 degrees. The first piece of information that we've needed. So this angle right there is 25.82 degrees. Cool. So let's continue with seeing if we can figure out what this T1 is here. Now we've got two equations in it and a whole bunch of things we don't know. So your mathematical skills should all be up to the point where we can see we've got two equations, a bunch of unknowns. Well, we're going to plug something in here. It's going to give us two equations, two unknowns, so we're going to substitute and solve. So let's plug some stuff in here. We're going to plug that value for theta in. So I'm going to get T1 cos phi equals 75 cos of 25.82. I'm not going to solve this yet. I'm going to leave it like this. This is exact form. There's no rounding. That is how I would recommend you approach that. So then T1 sine phi plus 75 sine of 25.82 is going to equal 49. Well, I guess we could make your life a little bit easier here. Just to save some space here, T1 cos phi. If you do actually solve this thing, 75 cos of 25.82, you're going to get 67.524. And then this guy here, if we isolate for T1 sine phi, we subtract, this thing is just a number, we subtract it over here, so that's going to equal 49 minus 75 sine 25.82. We're going to get that T1 sine phi is going to equal, I got 16.358. Now, what do you do? There's a technique. If you haven't taken Pre-Calc 12 yet, this is going to be a new technique for you. One of the things I told you once upon a time was that tan theta, again, this is for those of you who have not taken Pre-Calc 12, this might be new to you. Tan theta equals sine theta over cos theta, but we need that identity here. So what we're going to do is we're going to take this equation and we're going to divide it by this equation here. So I'm going to get T1 sine phi equals 16.358. We're going to divide that by this equation over here. Now this is a technique that you should have seen when solving systems of linear equations. I want to say either in grade 10 or grade 11. Don't remember where it shows up. But it's a technique you should have seen before. What this allows us to do is it actually allows us to cancel out T1. And then sine phi over cos phi is going to give us tan phi. So tan phi is going to be the 16.358 over 67.524. So phi is going to be the tan inverse of this, 16.358 over 67.524, which is going to give us an angle of 13.6 degrees. And now what we can do is we can take this this angle and plug it back into either one of these equations to find T1. It doesn't matter which one we use. I'm just going to take it and I'm going to plug it back in right here. So I'm going to get T1 times sine of 13.6 equals 16.358. And if you solve this for T1, you're going to get that T1 is 69.57 newtons. Oh, sorry, I'll zoom that out for you here. So there we go. We've used these ideas of static equilibrium. Static equilibrium is a pretty simple idea. It's not moving. But the implications there are pretty substantial. We've got my left forces equals my right forces, my up equals my down, and my clockwise equals my counterclockwise as far as my torques are concerned. And so what those assumptions allow us to do is all of this. This is the last example I'm going to do. The questions I'm going to assign to you guys for this section, I want to flip the page now, are going to be as follows. I want you to do 1 to 4 and 7. And if you're really bored, well, not even if you're really bored, if you're interested in a particular activity, you can go back and look at the previous example here. This shows up at this particular party trick has showed. I've seen it in university at gatherings of science students. The trick is to get both men and women in a kneeling position on a flat surface, then place a short object that's less than 10 centimeters tall, about 50 centimeters from the knees. The challenge is to place the arms behind the back and knock the object over using the nose, and then return to an upright position. Generally speaking, women can do this, though that's not always true, and generally speaking, men cannot. Again, generally. Again, why is this? And there's a whole bunch of reasons why this happens, and it's all surrounding the ideas of torque. So give this a shot. Let me know if you can do it or not. Yeah, we'll make this part of your homework. I want to know a response to this. Try this. See if you can do it. So you want a 5 centimeter high object, or an object less than 10 centimeters tall. Place it 50 centimeters from your knees. Put your arms behind your back. See if you can knock it over with your nose and return to an upright position. If you want to film a video of yourself doing this, this would be absolutely hilarious for our class to see. This is something that we would do if we were in class together. But again, we're online, so we can't. So give this a shot. Film yourself if you're brave, and post that to our Google Classroom. But this is absolutely your homework for today.